Okay, so in this video we're going to look at oxidation and reduction titrations, and we're specifically going to introduce the idea of them and look at the theory. So specifically we'll look at the properties of potassium permanganate, iron, sodium thiosulfate and iodine, because they are the main chemicals that are involved in oxidation and reduction titrations. So first we'll look at potassium permanganate. And potassium permanganate will sometimes be referred to as potassium permanganate 7, and that's got to do with its oxidation state. It has the chemical formula KMNO4. It's purple in colour and is a very powerful oxidizing agent. It's quite unstable, so it decomposes in the presence of sunlight, and it must be standardized by titration against a primary standard. It is a self-indicator, so in a titration where you're using potassium permanganate, you don't need an indicator. It changes colour from purple to colourless when it is acting as an oxidizing agent. How this works is the Mn7 ion, or as we would refer to it as Mn plus 7, it will gain 5 electrons in a titration to produce manganese 2, which is Mn2 plus. So if it is gaining electrons, it is being reduced, and that means it is an oxidizing agent, as I've said already. So for a reaction to occur, the permanganate must be acidified with sulfuric acid, and that is to give it H plus ions. And we use sulfuric acid because if we used hydrochloric acid, the chloride ions present may be oxidized to chlorine gas by the potassium permanganate. If sulfuric acid isn't added, or if the permanganate isn't acidified, what you'll get is you will get a reduction from Mn plus 7 to Mn plus 4, and this gives a brown colour, and that's a brown colour that you want to try to avoid, as it is an intermediate oxidation state. So you could have, I'm just going to go up to the top here, you would have Mn plus 7 to Mn plus 4 to Mn plus 2, and the Mn plus 7 is purple, the Mn plus 4 is brown, and the Mn plus 2 is colourless. So you want to avoid this Mn plus 4. You want to avoid the formation of a brown precipitate. It's important to read from the top of the meniscus when your potassium permanganate is in a burette, and this is due to the intense colour. So as I've said already, we can see that the MnO4 minus, that's when the manganese is in the plus 7 oxidation state, when it gets reduced to the Mn plus 2, it goes from purple to colourless. When we're doing a titration involving KMNO4, we know the endpoint is reached when we see a permanent pink colour being obtained in the conical flask. So when the KMNO4 has been added to the conical flask, it basically, it's purple in the burette. As it's added to the conical flask, it turns colourless because the oxidation reduction reaction is occurring. But once there's no more of the reactants left in the conical flask for the oxidation reduction to occur, the pink colour will start to show, and that means that the KMNO4 is no longer reacting. So that's why the endpoint is by the appearance of the permanent pale pink colour. It's also important to notice that KMNO4 is not a primary standard, and that means it's not possible to make an accurately known concentration solution by weighing out a sample and dissolving it in water. You can only find its concentration by a titration. So next we're going to look at iron compounds. So first of all, iron is in the Fe2+, iron will be a reducing agent in our experiments, and it will be very stable. In our experiments or in our titrations for oxidation reduction, when we're using iron, we use ammonium iron 2 sulfate as our source of Fe2 plus. Ammonium iron 2 sulfate is usually dissolved in water that contains sulfuric acid, and this is to prevent the iron 2 plus from reacting with the air to form iron 3 plus. Rather than just using iron 2 sulfate, we use the ammonium iron 2 sulfate because it can be attained by high purity. So the formula for ammonium iron 2 sulfate will always be given to you in an exam, but just for yourself to know, it's FeSO4.XH2O. So this .XH2O means that there is water molecules complexed with the ammonium iron sulfate. So if we look specifically of reactions between the manganese ion and the iron 2 plus, we know that KMnO4 is your oxidizing agent, and it will oxidize the iron 2 plus to iron 3 plus. The oxidizing agent here is the manganese, which is the MnO4. So what will happen is the manganese will, as it's an oxidizing agent, it will reduce, so it will gain 5 electrons to reduce your Mn plus 2 oxidation state, and at the same time the iron is being oxidized and it is losing an electron, so that's why we have a Fe2 plus going to Fe3 plus. Now if we look at this, we can see that the reducing agent only produces 1 electron, but the oxidizing agent requires 5, so that means we need 5 times as much iron as we do potassium permanganate in our experiment. So I've explained that here by saying we see that the manganese can accept 5 electrons, but iron can only lose 1. So balancing your equations gives you the following, where we have our balanced 5 irons reacting with every 1 manganese. So that means in general our ratio in our potassium permanganate and iron titrations will be a 1:5 ratio, which is MnO4 is to Fe2 plus. So this slide is very important for the first 2 experiments that we will look at, which is to prepare a standard solution of ammonium iron 2 sulfate and use this solution to standardize a potassium permanganate solution, and it's also important for the iron tablet experiment. So these are 2 separate videos that you can find in this unit. So it's important to look at iodine and sodium thiosulfate as well. Iodine and sodium thiosulfate are involved in 2 of our redox titrations that we do in our course, and that is to prepare a standard solution of sodium thiosulfate and standardize it by titration against a solution of iron, and also the percentage of sodium hypochlorite present in household bleach. So to begin, sodium thiosulfate is a reducing agent towards iodine, and it converts iodine molecules into iodide ions. The thiosulfate has the structure just revealed there, and sodium thiosulfate is a colourless state. So a solution of known concentration cannot be made by weighing out a sample and dissolving it in water. Instead, a sodium thiosulfate solution is standardized by titrating it against a standard iodine solution. So basically, to find its concentration, you must do a titration. Similarly for iodine, a standard solution of iodine can't be made by weighing either because it vaporizes. But what we can do is we can make a standard solution of iodine by reacting a standard solution of potassium permanganate with excess potassium iodide ions. Now, there's 2 good reasons why we would use excess potassium iodide. Firstly, by having the iodide ions in excess, it means that all of the potassium permanganate solution will react completely to produce our iodine. And secondly, the presence of the iodide ions helps to keep the iodine molecules that have been produced in solution. So, how can we determine the endpoint of an iodine thiosulfate titration? So, at the start, you will have a reddish-brown colour. However, as the titration proceeds, this will turn yellow, getting a paler and paler as the titration proceeds. So, once you get a straw or pale yellow colour, we need to add our indicator. Now, it's important that in an exam you would refer to this as a straw yellow colour. The indicator that we use in iodine and thiosulfate titrations is starch, and it causes the straw yellow colour to turn blue-black as the starch reacts with the remaining unreacted iodine molecules. So you continue the titration once you get your blue-black colour adding your indicator, and when all of the iodine molecules have been converted to iodide ions, the blue-black colour will disappear and the solution will turn colourless, and that's when you have your endpoint. So with your oxidation reduction titrations, you will be using the same first principles method as was done in the acid-base titrations. You can use the formula that we went through, but I'm going to be doing all of the calculations by first principles as outlined already. So that's it for this video. Have a read over the learning intention to make sure you understand everything we've gone through.